Hello?
Yeah, hello.
We'll continue.
Yeah.
So, related rates, I think I probably have explained you all the example problems. So, just go through the exercise. What are the questions that you have? We'll do some exercise problem that will help you understand the concepts clearly. Sorry, just going through the exercise problems.
Yes. Can we try number 8?
Y is equal to cosine x. Are you able to see the problem? Is that the one?
Yes.
Okay. Y is equal to cos x. Let's see what is asked here. Moving point. In exercises 5 to 8, a point is moving along the graph of a given function at the rate dx over dt. Find dy over dt for the given values of it. Let us see. So we have y is equal to cos x, dx over dt is equal to 4. So we have the function y is equal to cosine x. Just a moment, I'll just
Yeah, can we also try number 16?
Okay, so question number 8 you said, right? I'll explain. So y is equal to, so we have y is equal to cos x, and we have got dx divided by dt is equal to 4. Okay, so this is given here. We need to find out dy divided by dt. So this is what we have to find out the value. So differentiating, we will have dy over dt equals to cos x. If we differentiate, we get negative sin x times dx over dt. And for x is equal to pi over 6. So x is equal to pi divided by 6. We have uh, substituting dy over dt. Now we can just write here as dy over dt is equal to dx over dt is 4. So negative 4 sin x. So this is the answer. Now when you substitute x is equal to pi over 6, you will get negative 4 sin pi over 6. Negative 4 times sin pi over 6 is how much? Half. This is equal to negative 2. So this is the answer when x is equal to pi divided by 6. Again, similarly, you can apply for pi over 4 and pi over 3, and if you want, you can just find out the answer. Go through the solution. Any doubts you have, you ask me.
Yeah, it's clear.
So I think we'll be able to do it similarly for the remaining two parts.
Yes, it's the same thing. You just have to substitute the
Yes.
other angles, right?
The answer is negative 4 sin x. X is equal to what are the angle we substitute. Just get the
Yeah,
answer.
yeah. Okay, yeah, I think I can do it now for
Okay.
the other angles.
So what are the other questions you have? You can ask.
I asked number 16 as well.
Okay, number 16 here. All edges of a cube are expanding at a rate of 6 centimeters per second. So side of a cube is expanding here. How fast is the surface area changing when the edge is 2 centimeters and when the edge is 10 centimeters? So this is a very good example of a problem where in which you can understand the change in area perspective. Okay, so I'll just explain here. You will be able to understand here. So 16, maybe we are asked the surface area. So surface area formula, I can just take it as S. Okay, so S is equal to 6a square, where a is the side of the cube. So cube has three, of course they have three dimensions, but the parameter is just only one, the side, because it depends only on the side. On the side is what we have in three different directions. So all edges of the cube are expanding at the rate of 6 centimeters per second. How fast is the surface area changing when the edge is 2 centimeters? So how fast is the surface area changing? So when you differentiate this function with respect to t, so t in the sense with respect to the time, how much is the change? Okay, so we'll have ds over dt is equal to 12a times dA over dt. All edges of a cube are expanding at the rate of 6 because when the side of the cube is expanding, you'll be able to get to know the expansion of the surface area or volume or whatever it is that we need to find out with this dependent with the side. So that information is clearly given to us. All edges of a cube are expanding at the rate of 6 centimeters per second. So we are given dA over dt is equal to 6. By calculating, you have ds over dt is equal to 12a times 6, which is equal to 72a. The first part, when a is equal to how much is the surface area increasing. So ds over dt will be 72 multiplied by 2 gives you 144 centimeters square per minute. What is the unit here? Per second. Oh, per second. And the second part, when a is equal to 10, what could be the answer? 720 centimeters square per second. So you will be able to notice that the surface area does not increase uniformly because area, because when the side is increasing uniformly, area is like it's multiplied by itself. Okay, multiplied by a constant term, and volume increases even more. Okay, even faster. You'll be able to see as we have an a is 2 centimeters. The surface area is increasing at the rate of 140 per centimeter square per second at that moment because it changes. There will be a uniform change in the surface area. And when the A becomes 10, you see the surface area change becomes 720 centimeters square per second. You have the solution.
Yeah, it makes sense now.
Can you just tell me the next problem? Whatever questions you have.
Can we try number 41?
Linear versus angular speed. A petrol car is parked 50 feet from a long warehouse. The revolving light on top of the car turns at the rate of 30 revolutions per minute. How fast is the light beam moving along the wall when the beam makes an angle of 30 degrees, 60 degrees, and 70 degrees with a perpendicular line from the light to the wall? Okay, suppose you just have an idea here. The diagram here, will I be able to copy the diagram? Copy image. Piece by piece is what recording here. Will be okay. A patrol car is parked 50 feet from a long warehouse. The revolving light on top of the car turns at a rate of 30 revolutions per minute. How fast is the light beam moving along the wall when the beam makes angles of 30 degrees, 60 degrees, and 70 degrees with a perpendicular from the light to the wall? Okay. So this is 50 feet from the wall. I hope you are clear with the diagram, right?
Yes.
Okay. Now, the light beam, we can just make it as the length, the distance here. So light beam will be how much? Light beam, what we'll take it as y. So y square is equal to x square plus 50 square. Okay, so y is equal to x square plus 50 square to the power half. I can write this as x square plus 2500, the entire square root. I'll just write the power as half itself. I'll just do dy over dt. So this is equal to half 1 over square root of x square plus 2500 times 2x times differentiating x will have dx over dt. Now 2 cancels. So dy over dt is equal to x over square root of x square plus 2500 dx over dt. You may also be able to notice that this length of this, what do we say, length of this beam depends upon the value of theta. Is that right? And yes, of course, related to x as well. So I think the relation that I have written is wrong because theta plays an important role. So how am I going to take? So this is why if I take now, you see, y is equal to 50 is equal to y cos theta. Is that right? 50 is equal to y cos theta. Or y is equal to 50 secant theta. The 50 is fixed. What about x? So y is equal to x over sine theta. We'll take this itself. Okay. So y is equal to 50 secant theta. Just I'll write it here. Y is equal to 50 secant theta. Are you able to understand?
Yes, yeah, I can understand.
So y is equal to 50 secant theta. Verify once. Okay. So differentiating will have dy over dt equals 50 secant theta differentiation. Derivative will be secant theta tan theta times d theta over dt. Now d theta over dt we can find out as we have done earlier today. The problem that we did, right? Example number 6, suppose. And this is the problem that we did earlier. So the angle, what did we do? The same thing that we have to apply here also. Now, you see that the car is rotating at a rate of 30 revolutions per minute. So, 30 revolutions multiplied by, for every revolution, it's 2 pi. So, it will be 60 pi per minute. So, d theta divided by dt is 60 pi. So, 50 secant theta tan theta times 60 pi will be dy over dt. And dy over dt is what we'll find out because that's the speed. Speed means derivative of the, right? Speed is the first derivative. So, 50 secant theta tan theta. Okay. When theta is equal to 30 degrees. So 50 secant 30 degrees will be 2 over root 3. Is that right? And tan 30 will be 1 over root 3 times 60 pi. So 6000 divided by 3 pi equals to 2000 pi. Okay, so that will be the answer. So pi you can take 3.141 pi or 2/7. So you'll be able to get the value of the speed. It's feet here. So the speed will be 2005 feet per minute. Now, when the angle is 70 degrees or when the angle is 60 degrees, according to that, we can just try to calculate. Are you clear with the problem, the solution?
Wait, how did d theta over dt become 60 pi? Can you explain?
That's the speed of the angle. See, 30 revolutions per minute, have you read in the question? So for each revolution, we have got 2 pi of the angle change. So multiplying, you'll get 60 pi. This is the change of theta. Is that clear? We have the solution.
Yes.
Okay, next, which problem?
Yeah, those are all the questions I had for this lesson.
Okay, so we'll have review exercises, problem solving. We have got a good amount of problems that you have here. So next comes the applications of differentiation, next chapter 3. Okay. So before that, just take note of all the problems here. You have some time. After some time, you can just go through the review exercises as well as the problem solving. And wherever any questions are there, because so many problems are there, you have to practice those problems. Practicing those will help you to get a clear idea on the chapter of differentiation. Because if you are clear with this chapter, then the remaining chapters could be easy that you will be able to do it. Okay. Next comes here applications of differentiation. So these are all the sections that we will be covering. Extrema on an interval, Rolle's theorem and mean value theorem, increasing and decreasing functions in the first derivative test, concavity at the second derivative test, limits at infinity, summary of curves sketching, optimization problems, Newton's method, and differentials. Okay, let's go through with the first one, extrema on an interval. So extreme means towards the end. So it's either we'll be able to get some maximum or minimum of a curve at a certain stage. Okay, when we just consider the graph here, for example, and when we consider a curve, for example, you have a curve like this. For example, in the interval here, we'll be able to notice at this particular point, the curve reaches the maximum point. So this is what we call as the maximum. And what type of maximum? It's called the local maximum. And similarly, at this particular point, we'll have something called as local minimum. And we also have this particular point called as local maximum. And here we have local minimum. Now you may be observing, so this is number 1 I'll take, this is number 2 I'll take. So local maximum at number 1 is bigger than the local maximum at number 2. That does not mean that this place will not become local maximum, because for this particular point, you're just going to take a small interval within this to check which of these elements is having the highest value. And definitely it will be only the maximum point which will have it. Okay. And also we have global maximum and global minimum depending upon the graph, depending upon the curve that we have. There are some problems in some curves which does not have a global maximum but has a global minimum. For example, if you consider this curve, this simple curve that we see here, a parabola, a quadratic parabola. So a quadratic curve is something like this, and you see that at this particular point, you'll be able to notice that the curve reaches the minimum, and this is true for any real interval that we take. Any real interval, you'll be able to observe that there will not be any point other than this particular point. We'll take it as negative b over a, at which the given curve gets a minimum value. Able to understand? So this is of course we can call it as local maximum as well, but generally we can call this as a global maximum, or this is the only minimum. I'm saying with minimum. This is the only minimum that we can have in this graph. If a function is continuously increasing, for example, if you just take a function which is continuously increasing like this, now whatever the interval that we take, for example, if we just have an interval here, you'll be able to notice that the right hand side endpoint has the maximum possible value, and left hand side endpoint will have the minimum possible value at that particular interval. And when the function is increasing throughout, we see that f of x is equal to negative infinity, or even true for some positive um, values. I hope you are able to understand.
Yeah, it makes sense.
So probably like for an increasing or decreasing functions, we'll have mostly endpoint towards the extrema. So that's what we call. I mean, extrema towards the endpoint. That's what we call it as endpoint extrema. When you're saying about the endpoint, most probably you just have to take the interval to be a closed interval, not an open interval. If you're taking open interval, it is not possible for us to uh, find out towards the endpoints of any interval where the given. Okay. The extreme value theorem you can see here that if f is a continuous function on a closed interval a comma b, then f has both a minimum and a maximum on the interval. If f is a function which is continuous, you have to know that we we just have a minimum value and a maximum value. What about relative extrema? Probably in the middle. That's what we say, local maximum, local minimum. Those we can compare related to this concept called relative extrema. Okay, we'll do example number 1. The value of the derivative at relative extrema. Okay, I'll just explain one more important point here, probably graph. Okay, you see here. So this is an increasing function at this interval. So at increasing function, the first derivative, so f dash will be positive, and as the decreasing function, f dash will be negative. So once again, here f dash is positive, and here f dash is negative. So here we have f dash positive. Now at this point, you see that f dash equals to 0 at all the points where it is changing. Excuse me. Where this function is changing, so wherever the function changes from increasing to decreasing, like here, or decreasing to increasing, like here. So at that particular point, okay, we'll see example number 1. The value of the derivative at Just a moment. Okay, so we'll continue. F of x is equal to 9 of x square minus 3 divided by x cube. So we'll do the first derivative. So what can we do? We can expand here. 9x squared minus 27 over x cube is equal to 9 over x minus 27 over x cube. So differentiating these functions will be very fast. So f dash of x, the first derivative will be negative 9 over x squared plus 27 times 3 will be 81 over x to the power of. And when we equate it to 0, we'll get the value of x, at which we can find out that this curve has a critical point. This is what we call it as a critical point. So critical point is a point where the increasing function converts into a decreasing function or vice versa, or we'll call it as a point of inflection. So 9 over x square is equal to, in fact, 9 over x square the whole square. Is that right? So 9 over x square cannot be 0, so we can cancel it off. So we'll have 9 over x square is equal to 1. We get x square is equal to 9. X is equal to plus or minus 3. X is equal to plus or minus 3 is what we have.
Yeah, this is the example's clear.
Are you clear with this problem?
Yes.
We will be getting the value of x as 3 or negative 3. Is that right? We'll get that. And okay, so these are different functions. Actually, I thought this is the same function for all the three functions. Okay. And there are some locations or some characteristics in which the function is not differentiable. For example, you can just observe here whenever we have a graph where the graph is just moving on somewhere and then it takes a sharp turn. It may not be two lines, it can be even curves also. For example, we have a curve like this curve. We have a curve like this is going on, and then suddenly a turn is just going on. It won't be like this, but still okay. Sudden turn, a curve is going on like this. So at this point, we have a sudden turn. So you will not be able to find out the derivative at this particular point. So this function is not, no function will be differentiable at any sharp change here. because we see derivative as an instrument to calculate the rate of change. So, for example, if I have this function at these two intervals, any point if I take, you'll be able to notice from the left hand side or from the right hand side, you'll be able to notice that the value gets closer to the value which is already given here, right? So, but when I have it here, for example, or when I just have it over here, then just take these 2 points, you may observe that both the values are equal. But as you get closer and closer, you will not be able to find out that particular characteristic because the change is this is not a regular change or a usual change that we'll be able to see usually, but a sudden drastic change. Even in a small interval, if you're having a sudden change, this will not be, or this will just, we can say that it will affect the definition of a differentiability of the function. So we can say that wherever a curve has a sharp turn, you will be able to observe that the function will not be differentiable at that particular point. Absolute value of x, the second part, absolute value of x is a very good example. You see, it's coming down and suddenly it starts increasing here. The change is not gradual, the change is sudden. Okay, so these type of graphs will just give us a very good example of the differentiability of the function. See, the curve is going on at sudden change. These type of places, the derivative does not exist. Next section, finding extreme on a closed interval. It's simple here. For example, we just go through the. Okay, we'll just do example number 2 that will help us understand very clearly how to find extrema of any function at closed interval. Example number 2 here. F of x is equal to 3x to the 4, 3x to the 4 minus 4x cube. Okay, that's what we have right here. So, on the interval -1 comma 2, this is the interval which is given to us. The interval is -1 comma 2. Now, so f of -1 will calculate. F of -1 will be 3 plus 4, which is equal to 7. F of 2 is equal to 3 times 16 minus 4 times 8. 48 minus 32 gives you 16. Also, we'll calculate f of x as that, or we'll just find out the first derivative. So f dash of x, which is equal to 12x cube minus 12x square. So it is equal to 12x of x minus 1. And this becomes 0 at x is equal to 0, x is equal to 1. So f of 0, you get 0, and f of 1, you will get 3 minus 4 is equal to -1. So you'll be able to notice that f of 1, we have -1 as the global minimum. So how am I saying it's global minimum? There are infinite number of values possible between -1 and 2. At 1, we get the answer -1, and I'm saying it to be as a global minimum. So how do I say that? If you want, you can just uh, find out. That's what we did, right? Find out the derivative. You see here. So the critical value will be either 0 or 1. These are the only two places in which we'll be getting the critical value. Is that clear? Any questions till now?
No.
So we have to find out the extreme, so maximum and minimum values. You see that at x is equal to 0 and 1. So x is equal to 0, probably we may not know whether it is local maximum or local minimum. Yeah, definitely it's not global minimum because you got -1 here. So this cannot be a global minimum and this cannot be global maximum either. Because you see at endpoints we see f of -1 is 7 and f of 2 is 16. So 16 is the global maximum. You see, when x is greater than 1, what happens? So this expression is positive. So after 1, the function is increasing. So when f of 1 is equal to -1 and f of 2 is equal to 16, the value is increasing from -1 to 16 only. So it is not possible for the value to go from -1 to some higher value and then come back to 16. Because from you see that the first derivative is positive, that means the function should be an increasing function. Are you able to get the idea? All the critical numbers at the left endpoint and the right endpoint will just calculate, and which of these is the least will get global, like we can say like a global minimum award, and which of these is maximum will get a global maximum award, like that you can just observe. Okay, so these are the different extrema that we can calculate. So any questions? So probably we'll just do more problems on this. We have got some more, two more problems. So we'll do these two problems and more problems from the exercise. So next class, we'll continue the next class. Any doubts you've got till now? Any questions?
As of right now, no. I think I need to review this lesson a little bit more, and then
Okay,
I'll see if
definitely.
I have any doubts.
And before that, chapter number 2, you've got review exercises and problem solving section. Okay, we have to go through that. And also even the exercises from each and every part, we have to practice them. So you'll be able to get a very clear idea on the differentiation section, and then the applications of differentiation is equally more important than the previous previous chapter. Okay, and next
Okay.
comes integration, which will be a new topic. Okay, tell me.
Okay, yeah.
I heard you saying something.
No, I wasn't saying anything about, like, I wasn't asking a question.
Okay, so before the next class, I just want you to practice as many problems as possible whenever you are free. Try to do the best in terms of solving the problems. Okay, that will be of a good help to you. Okay, then we'll finish today. We'll continue in the next class. Thank you.